Hello, madam. We are from Group 26 are going to present our project. First of all, we will go through project question 1, which is about simulating basic operation of a reduced instruction set computing CPU architecture. Before we go into designing and running a CPU simulator, we need to understand the architecture of the CPU. This includes its main components, such as the program counter, instruction register, general purpose registers, arithmetic logic unit, and memory. Each of these components play an important role in how the CPU fetch, decodes, and executes instruction. Having a good understanding of these parts will help us see how the CPU operates step by step during the simulation. The program counter is a 16-bit register that stores the address of the next instruction the CPU needs to execute. It's also commonly known as the instruction counter, instruction pointer, or instruction address register. After each instruction is processed, the PC automatically updates to point to the next one. It increases by 1 every time a bit is fetched, and if the system is restarted or reset, the PC will return to 0 and start the process again. The instruction register holds the current instruction that has just been fetched from memory. It stores the entire instruction, including both the opcode and the address, usually in binary form. The instruction register keeps this instruction temporarily while the CPU decodes it to understand what operation needs to be done. Only after decoding the contents of the instruction register can the CPU move on to execute the instruction. The general purpose registers are small storage areas inside the CPU labeled as R0 to R3 in our simulation. They temporarily hold data that's needed for operations like calculations or memory transfers. For example, when the CPU adds 2 numbers, it first loads them into these registers. After the operation, the result is also stored in one of the registers. Using registers helps speed up processing because accessing them is much faster than accessing main memory. The arithmetic logic unit, or ALU, is the part of the CPU that handles basic calculations like addition and subtraction. It takes values from 2 registers, performs the operation, and then stores the result back into one of the registers. The ALU is what allows the CPU to process data and make comparisons, which are essential in most tasks a computer performs. In our simulation, memory acts like 64 numbered slots, and each slot can store one value. It holds both data like numbers and instruction for the CPU to follow. For example, if memory at address 10 contains the value 5, the instruction load R010 will move that value into register R0. Instructions like load and store are used to transfer data between memory and the CPU's registers.
We go towards the CPU instruction set. So we create an instruction set that consists of load, store, add, sub, jmp, and halt in the CPU. So, based on the table, the mnemonic for load, the opcode is 0001, register operand 0010. Description is to load data from memory to register. An example is the load R0 to 10. For store, the opcode is 0010, register operand is 0101. The description is to store data from register to memory. An example is to store R0 to 12. For add, the opcode is 0011, register operand is 0001. Description is to add values of 2 registers. An example would be to add register 2, R0, R1. For sub, the opcode is 0100, the register operand is 0011. The description is to subtract one register value from another. An example is to sub R2, R0, R1. For GMP, the opcode is 0101, the register operand is 000, which means it doesn't exist. And the description is to jump to a specific instruction index. Example is GMP3. And for the final one, the final mnemonic halt, the opcode is 1111, the register operand is 0000, which means it doesn't exist, and the description is to stop CPU execution. An example would be halt. Moving on, we go towards the CPU registers. For register 0, the binary code is 0000. The description is general purpose register 0. R1 has a binary code of 0001. It's the general purpose register 1. For R2, it has a binary code of 0010, which is the general purpose register 2. For R3, it has the binary code of 0011, with the description of general purpose register 3. For register IR, it is the instruction register. It stores the code instruction. And for register PC, it is the program counter. It stores the address of the next instruction.
Alright, so continuing to CPU simulation, our CPU simulator is built using the C++ programming language, which is well known for its ability to handle low-level operations similar to how real hardware works. The CPU uses a simple assembly-like instruction format that is easy to read and understand, even for beginners. And each instruction is written as a string in the program, and the simulator reads and runs these instructions step by step, just like a real CPU would during the fetch, decode, execute cycle. And this approach makes it easier for the students to learn how the CPUs process instruction in a clear and straightforward way. So this program includes a small instruction set, which is load, store, add, sub, jump, and halt. There are 4 general purpose registers, which is the R0, R1, R2, and R3, which are declared and initialized. And the memory is represented as a 64 element array, and each instruction is stored as a string and parsed during the execution. In the CPU program, there are 4 core components which are implemented, which is the program counter, the instruction register, the registers, and the memory. So the first one, the program counter, it is used inside the main loop to control the instruction flow, which you can see from the code we use in the program below. And the second one is the instruction register, IR, which is used to be updated at the start of every loop iterations. Thirdly, the registers, it is initialized in the main functions, which is to register the R0, R1, R2, and R3. And lastly, there's the memory, which is used to store values referenced in the instructions, such as the memory 10 and memory 11, which is 5 and 7 respectively. Alright, lastly, onto the instruction execution function. The instruction cycle in the simulation includes multiple stages that are executed within the main loop of the program. Below is a breakdown of the steps along with the corresponding C++ code that contributes to each stage. So there are actually 4 functions, which is the fetch, the decode and execute, the print state, and the advanced program counter. So the first one, fetch, this stage retrieves the next instruction from the program vector using the current value of the program counter PC and stores it in the instruction register, which you can see from the while loop below. Onto the second one, the decode and execute. The instruction in IR is passed to the decode execute function, which handles the parsing and the execution based on the instruction type, which is the load, add, sub, store, jump, and halt. And thirdly, the print state. And after the instruction is executed, the current state of the CPU is displayed, including the values of the PC, IR, and the 4 registers. This is done using the print state function. And lastly, we have the advanced program counters, PC. And after executing an instruction, the program counter is incremented to point to the next instruction. This ensures that the CPU continues executing the next line in sequence, unless altered by a control instruction such as jump. And this cycle repeats until a halt instruction is encountered or all instructions has been executed. Alright, now we're moving on to the demo part of the presentation. This is the program of the CPU simulation that we made in C++. And as stated from the presentation earlier, we have the CPU components, which is the program counter, the instruction register, the registers, and the memory. Moving on, we have the decode execute function, which have the following instruction sets, which is the load, store, add, sub, jump, and halt. And we also have the print state function, which is to print out the output. And continuing to the main function, we have the registers R0 to R3, which is declared as 0. And we have the memory of 10 and 11, which have the value of 5 and 7 respectively. And we have the vector program as the sample instruction. For example, the load R0, 10. And we have the while loop for the fetch function. And lastly, to output the last final memory state. And if we run the program, it would show that starting the RISCE CPU simulation, which start with a PC count, we start with a program counter of 0, and the instruction register is loading up is load R0 10, and the registers is in the default value, which is 0. And after that, it will load the R0 from memory 10, which is 5, and the program counter will increment by 1, and continuing to the instruction register of load R1 11, which would load the R1 from memory 11 as 7 with a value of 7, and the program counter will increment again, and the instruction register will continue to put out an instruction of add R2, R0, R1, which add R1 and R0 into R2, which is 12. Continuing, and then it will store the R2 value into a memory of 12, which is 12. And lastly, the final output will show that the final memory state of address 10 to 13, which is in memory 10 is still 5 and memory 11 is still 7, but in memory 12 it shows that it's 12, which is from the earlier instruction above. And memory 13 is 0 because we didn't put any value in it. Right, that's all for demonstration. Thank you.
So hello everyone, my name is Dylan, and now I will be presenting the question 2 of the cache simulation. So for this question 2, we will tasked to simulate how cache memory behave under different configuration and how it affect the performance in terms of the hit rate, miss rate, and memory access efficiency. So for question 2, we built a custom cache simulator and use a matrix multiplication as the workload to generate memory access pattern. The goal for this question is to analyze how different cache size and displacement policy affect the overall performance of the mapping technique that we choose. The cache memory concept. So what is a cache memory? A cache memory is a small and fast memory located close to the CPU. It is stored frequently accessed data, so the CPU doesn't have to fetch everything from the slower main memory. This reduces the time needed to access data from the main memory. Usually, cache is classified into multiple level cache, which are level 1 cache. This is the fastest and the smallest, and it is located in the CPU core. Next one, we have level 2 cache. This level cache is larger but slightly slower than L1 cache. And then level 3 cache. Level 3 cache is shared across the cores, and it is designed to improve the L1 and L2 performance. The chosen mapping technique. So for this project, we use the set associative mapping, specifically a two-way set associative cache. In this method, the cache is divided into set, and each memory block mapped to one set, but can go only into any line within that set. So why do we choose this set associative mapping technique instead of other two, which is direct map or fully associative? So set associative mapping gives us a balanced speed and flexibility as it combines the strength of direct map and fully associative. This mapping technique is commonly used in real-world CPU design. For the chosen replacement policy, so we tested 3 different replacement policies to see how they affect the cache performance. The first one, we have LRU, least recently used. This policy replaces the block that hasn't been used for the longest time in the memory, and it is good for temporal locality. The second one, we have first in first out. This replacement policy replaces the oldest item in the cache with the new one, and it is simple, but it may also remove the useful data that we might use in the future. And then the third policy, we have random replacement. This policy evicts a randomly selected block, and it is simple, fast, but the performance depends on the access pattern. Simulation setup. Our simulation workload was a 10 times 10 metric multiplication task, which is memory intensive and involved a lot of repeated access to the same data. This generated about 400 memory per access run, which was perfect for testing how well the cache handle repetitive pattern. So here's the setup that we use. For the cache size, we use 4 KB, 16 KB, and 64 KB. For the block size, we use 16 byte, 64 byte, and 128 byte. And then for the replacement policy, as we mentioned earlier, we use the LRU, first in first out, and random. So this allowed us to compare the different configuration and see how they affect the hit rate, miss rate, and overall memory access performance.
Hi there, my name is Matthias and I'll be explaining about our cache simulation results. To start things off, in a 4 KB cache simulation, larger block sizes lead to a very high miss rates with LRU and FIFO, while random replacement policy offers only a partial improvement. As for performance comparison, LRU and FIFO completely fail with larger blocks. Random replacement helps but can fully compensate. Next, for 16 KB cache sizes, its hit miss rates only affects random replacement, where it offers moderate performance with large block sizes. Deterministic policies, LRU and FIFO, suffer 100% miss rates beyond 16 bytes of blocks in a 16 KB cache simulation. For performance, despite a larger capacity than 4 KB, a 16 KB cache still suffers from poor performance with larger block sizes under LRU and FIFO. Finally, for 64 KB cache simulation, the performance is uniform regardless of the replacement policy. Minor access penalties indicate efficient handling of both temporal and spatial locality. As for its performance comparison, a larger cache size almost nullifies the adverse effects of larger block sizes, delivering excellent performance regardless of the replacement policy.
Okay, here's a quick demo for our custom coding. First, we compile and run the code. Then you can see the interface for our custom coding. Here for cache size, we use 4 KB, but here as a parameter we set, we use byte for 0.96, and for block size we use 16 bytes, and then associative we use associative of 2, then a policy we use 0 as our LRU. Okay, here we can see the performance report as shown. The total access is 192, hits 132, misses 60, and our hit rate and miss rate. As shown, hit rate depends on how well the access pattern aligns with our cache configuration. And here also, our execution time is 0 millisecond, which our see the whole observation in a pattern, we can conclude that our simulation code cannot produce a precise execution time for the cache simulation.